Hello again out there in remote learning land. Today we're going to chat about what happens when all that water from rain, right, different climates we've been talking about, what happens when all that water hits the ground, right? You know, if it doesn't have the ability to get in the ground, you get a runoff flooding scenario. And that, of course, can cause a lot of damage and distress, and we'll talk about that today. Also, different types of soils allow different amounts of water to go in at different rates, and that, of course, can affect flooding in your area. So definitely things you want to know about before purchasing a home or moving someplace, because flooding, of course, can, you know, destroy entire homes in the blink of an eye. Okay? Hopefully you're working hard on those Regents Do Now questions. Let's get started. All right, the first clip I wanted to show you was a flood occurred in Atlanta several years back. I want you to think about how come the water isn't getting in the ground, right? Why does they have all this flooding? Because if you look at these pictures here, right, the ground does have air spaces for the water to get in. So ask yourself, what's going on in this scenario?
Across Atlanta, it was a day of frightening flash flooding and desperate pleas for help. Families like the Thompsons, trapped inside their home until rescue workers saved them.
Yeah, I feel like I'm having an anxiety attack, like really.
Anxiety is rising with floodwaters across much of North Georgia. Rains have been relentless. Some areas have seen 20 inches fall just since Saturday.
I've been here for 35 years and it's never been this high.
Rushing water swept cars off low-lying roads, killing at least 4 people. This man watched his neighbor float off in her minivan.
I couldn't see more than 3 feet in front of me. I mean, it was just a complete chaos, and I can't imagine what she went through, especially in the last moments of her life.
Entire neighborhoods were underwater, leaving lives in ruin.
Most of these people ain't got nothing as it is. And this is all they got. Now they're fixing to lose it. This is all washing away.
It wasn't just Georgia. Near Henderson, North Carolina, the Mud Creek poured over its banks. Bibb County, Alabama saw a foot of rain in 24 hours. Across much of the southeast, torrential rains canceled school, made commutes impossible, and stranded people like Johnny Roberts. His Jeep disappeared from his driveway.
I came home, I got a missing Jeep.
What do you mean you have a missing Jeep?
It floated down the creek.
Many of those flood victims need relief fast. They won't find it in the forecast. Much of North Georgia is expecting another 4 inches of rain overnight. Mark Strausman, CBS News, Atlanta.
So yeah, that's a lot of rain, folks. You heard 12 inches in 24 hours, 20 inches in a couple days. That is a lot of rain, and water, as you know, goes toward lower areas, and then it piles up. So what starts, you know, you hear 12 inches of rain, oh, not too bad. But in the lower areas, that rises like filling a swimming pool, and you have several feet. And that, of course, brings lots and lots of problems. So we're going to talk about, you know, what happens with this water. Why can't it get in the ground sometimes, not other times? What are the variables there? Well, check it out. Porosity is a key term here. Porosity talks about the percent of airspace in the ground. And the more airspace there is, well, of course, the more water it can hold when it rains. All right, so make sure you read your definitions there. All right, the amount of empty space in the ground, that's what porosity is. And there are a couple of factors that affect it. All right, we'll start out with the shape of the particles in the soil. If they're round, you tend to have more air spaces between them, so water can get in easier. But if they're angular, then they're kind of odd-shaped, kind of closed off, and you can't get the water into the ground as easily. So this would have a more flooding scenario. All right? Then you have packing, right? How loosely or tightly the ground is packed. When you plant, you know, a flower or a shrub, they tell you don't pack the soil around it too tight, right? The water can't get in. So a loose pack allows water to get in, but a tight pack, of course, the water can't get in as quickly. You'll get more flooding in this scenario as well. And then there's sorting. Look at the difference here. These are all the same size. These are all different sizes. Well, if it's a well-sorted sample, water tends to be able to get in easier. But if it's a mixed sample here, you can see all the air spaces are filled in by the smaller sediments. and you get lots more flooding in this scenario. So these three here with low porosity would mean more flooding as well. Okay? How is it affected by grain size? Well, if you take a look, these are three different grains, but they're all sorted, right? These are all small, all medium, all big. And if you literally sat there and counted up the air spaces here, let's say you had 20 here, right? Well, over here, maybe you have 50, and over here, maybe you have 100. But these are 100 small ones. These are only 20 big ones, but it balances out. So the graph would look like this. No matter what size you have, as long as it's sorted, then the porosity would stay the same. Okay? Grain size does not affect porosity as long as you have the same, it's a sorted sample. Okay? Okay. Check this out. This is a great little visual. There are 4 different sediments here, right? Going from big to small. Gravel, sand, silt, clay. And they're going to pour water in, and then you'll see how fast the water gets in, right? We call that how permeable it is. Well, check this out. Here comes the water. And look at how fast it goes through the gravel, and it's already pouring out, right? Finally, the sand, the silt's even slower, and you'll get a slow drip. But look at the clay, folks, right? Nothing going down there. Clay is very, very, very small, tightly packed particles, so the water can't really get through it. A lot of people whose homes are built on top of clay will get a lot of flooding in their basement because when it rains, the water can't get through the clay, so it comes into the foundation of the house. All right? That's when you got to dig one of those French drains or some other kind of remediation to keep the water from getting in your house. All right, we'll run that one more time there. Check it out. Fill up all of them with the same amount of water, and look at how fast that goes down, right? That's a quick rate of infiltration. It's very permeable. Whereas over there, almost no infiltration at all. That is impermeable. Okay? Okay. So there we go. Permeability, get your definition down there. How well fluid can pass through a material, and the rate, of course, is how fast it does that. Similar chart as before, but now we're changing, from porosity to permeability. If you have large sizes, you're more permeable, less flooding. Smaller sizes, it's a little bit less permeable, so more flooding. Over here, the packing scenario, if it's a loose pack, well, then the water can get in, right? It's high permeability. But if it's a tight pack, well, then obviously it's less permeable. Sorting, once again, if it's well sorted, it'll be more permeable. And if it's poorly sorted, it'll be low permeability. Again, these all result in flooding. These assist with infiltration, water getting in the ground. Okay, make sure you get that down there. Check out the graphs. See if you can complete these on your own. Hit pause. Okay, we're talking about particle size versus permeability. Well, the bigger the particle sizes, you get those big gaps between the rocks, it'll become more permeable. All right? Infiltration, well, if there's more infiltration, it must have been more permeable as well, so you get another direct relationship. Okay, make sure you can say those as statements when you make these graphs, right? Always start with the x-axis. As particle size does this, permeability does that. As infiltration does this, permeability does that. Start with the x-axis. And capillarity, our last one here, this is a fun one, right? Water's ability to climb upward. Maybe you've all taken some white carnations, white flowers, put them in different food coloring. And you will turn those white flowers different colors. All right, kind of a neat little experiment there. You've all seen a paper towel absorb more water. That's called capillarity. Okay, watch carefully. The tight pack versus the small particles versus the big particles. Watch the race. Boom. Right, not much competition there. Let's do it again. Boom. Look at how much faster the water climbs up in the smaller particles. So the smaller the particles are, the greater the capillarity is, right? It climbs up faster. So make sure you get that all in your notes there. On the side, if the particle size gets bigger, like this one here, then there's less capillarity, right? It can't climb up as easily. It's got to jump from big space to big space, and water doesn't jump well. Whereas over here, you got these little spaces, and the water can kind of cling to things. You know, water likes to stick to itself. It likes to stick to your counter, right? They call that adhesion and cohesion. Well, that's what's going on here. It's sticking to things, and if they're tightly and packed and small, it's easier for it to stick and climb up. Okay? Over here, right, if you increase the particle size, you'll retain less water, right? There's literally less water in here because it didn't climb up. So you're retaining, you're hanging on to less water. All right, make sure you get your notes in there. All right. Like always, we have the summary questions you guys are cranking on. Please refer back to the lesson if you get stuck on any of them, and we'll go through it in just a few moments. I'll meet you back in a minute.